So, in this class we will first review the last lecture and then we will go through the new concepts. So, we was in the last class we looked at what is the effect of doping on the conductivity, and we found that we are looking at magnesium oxide, and what we found was that upon doping the conductivity changes significantly. So, there is a change in the ratio of electronic to ionic conductivity and how the nature of conduction changes. The main thing that we discussed in the last lecture was ionic conduction, and we derived a quantitative model for that. And as we can see here, we took for example, you can consider these positions as at regular ionic positions, and between these ionic positions you have some sites which are empty, which are nothing but vacant sites, and it is the migration of these vacant sites in either direction which gives rise to conduction. So, in the absence of electric field, the barrier to migration is, let us say, E A on either side, and the probability of migrating on either side is equal. Now, when you apply a finite electric field, there is a tilt in the potential well, let us say towards the right. As a result, the barrier on one side is decreased by a magnitude delta E A, and it is increased by a magnitude delta E A on the other side, since the potential wells are symmetric. Now, as a result you have, so as a result of application of external field, this probability term F, that gets modified. Now, what happens is the probability, so as a result of unequal barrier to be crossed on either side, the probability in this case to move into right is higher as compared to move in the left. As a result, the carriers or the defects acquire an average velocity, and this velocity can then be incorporated into the expression for current density, and this current density, if you modify it, what you get is an expression J is equal to sigma E, which can be equated to J is equal to sigma E, and from this you can work out what sigma is. And as you can see, that sigma is nothing but some pre-exponential factor multiplied by exponential of minus E A by k T, and this is very similar to the expression that we derived from the diffusivity expression. So, these two expressions are similar, so which tells that our model is not incorrect, it is correct model. And this can be further verified experimentally. You can compare the values of activation energies, the values obtained by diffusivity measurements are pretty similar to the values which are obtained from the conduction measurements. So, this validates again the model that we discussed. And then we looked at what are the good ionic conductors. So, one of the examples are beta aluminas, then you have many other oxides. All of these have different activation energies. Typically, good ionic conductors have low activation energies, and there are other oxides which have very highly insulating character, such as aluminum oxide, yttrium oxide, etc., and these have very low conductivity values. And then we looked at the cases of glasses. In case of glasses, the resistivity or conductivity is important, because glasses need to be melted in the furnace, where resistivity of the glasses can be used as a tool for resistive heating of the glasses, so that they are melted in the furnace itself to save the costs. And to control the resistivity of these glasses, you can add modifier ions such as sodium or potassium or lithium, and as well as the alkali earth ions, and depending upon the size of and type of ion, there will be a certain increase or decrease in the resistivity, as we discussed last time. Typically, what you see is that as the size of the ion increases, the resistivity also goes up. So, this is the bigger ions actually act as a blockers. So, they block the ionic movement. And in the same category you have something called as fast ion conductor, and these fast ion conductors are basically very highly conducting oxides or other ceramic materials which have conductivities higher than 10⁻² per ohm centimeter. And this is because in these materials the number of actually mobile ions is a significant proportion of number of potentially mobile ions, which is very small in normal ionic solid. So, you intrinsically the fast ion conductors which are intrinsically FICs could be your halides and chalcodenides of, for example, silver. You can have alkali metal conductors like beta aluminas. These are intrinsically very mobile structures because of presence of smaller mobile ions. And then you can have extrinsic FICs where you can convert otherwise insulating material into a good conductor, such as zirconium oxide doped with yttrium oxide or calcium oxide by means of defects, and also since there is an open structure in the compound. And then we looked at some of the conducting ions which participate in these oxides. Now, what will we do in this lecture is we will look at some other aspects of ionic conduction, and one of these is electrochemical potential. Now, electrochemical potential, as the name suggests, is a combined effect of electrical potential and chemical potential. Now, usually what happens in ionic systems, you have both electrical as well as chemical gradients present. Now, this could be because chemical gradients is because of differences, for example, in the composition, etc., and electrical gradient comes because of the charged nature of many of these defects. So, this non-uniform distribution of defects in a solid which is bound to occur in any given solid, inhomogeneity is something which is which occurs naturally in most of the materials. This gives rise to internal electric field. So, even if you do not apply an external electric field, you have a built in electric field within the material because of this non-homogeneous distribution of electric charges which is associated with the defects. And then you can always have chemical potential, which is nothing but thermodynamic potential, which would arise because of compositional gradients. So, the total mass transport now in such a case, the total driving force behind such a mass transport is not only the chemical force, but also this electrical force, and this is what is called as total electrochemical potential. Sum is called as electrochemical potential. So, let us assume we have a species I. Okay, let us define this as species I, which could be nothing but a defect. So, electrochemical potential of this species I is eta I. So, eta I is something which I have defined as the electrochemical potential, and this eta I is nothing but sum of chemical plus electrical potential, and this becomes equal to nothing but mu I, which is chemical potential, plus electrical potential. This becomes equal to Z I F delta phi. Okay. And so, where Z I is nothing but your charge, F is nothing but Faraday's constant, which is nothing but 96,500 coulombs per mole, 96,500 coulombs per mole, and delta phi is nothing but your potential gradient. And now, we know that the virtual force on the particle is, so the virtual force as we defined earlier on the, let us say we call it as a particle, I mean you can, it is nothing but an entity. Virtual force on the particle I is nothing but negative gradient of eta I. So, virtual force F I is given as minus of 1 by N A into d eta I by dx. This is how we defined this virtual force earlier in the beginning of this module. How do you now? Flux is nothing but J. So, if I write now flux J I as nothing but C I into Vi. It is a product of concentration per unit volume multiplied by the velocity, and this, since we know how velocity is related to force, Ci into Bi into Fi. Okay. So, this is the relation that we derived earlier. Flux is nothing but product of composition and velocity, and this becomes equal to your concentration multiplied by Vi is equal to Bi into Fi, which is nothing but mobility into force, and this becomes your flux expression. So, now if you replace the Fi from the above expression, this Ji can be written as minus of Ci Pi divided by Na into d eta I by dx. Okay. So, up to this point we are fine. So, now if we look at the expression, so this shows that what is flux made of? The flux is nothing but a function. So, flux is nothing but a derivative of electrochemical potential. So, or related to the derivative of electrochemical potential. So, alternatively this Ji can be written as minus of Ci Bi divided by Na into d mu I by dx plus Zi f d phi by dx. Okay. So, Ji is function of d mu I by dx as well as d phi by dx. So, this is a basic expression that we will now use to in case of ionic conductors. So, this is your chemical term and this is your electrical term. Okay. Now, what we will do is that we will derive a equation which is very pertinent to ionic systems and which is called as Nernst equation. So, this now what happens is when you have such a system in which your flux is related to electric field. Now, what happens is when you have a chemical potential gradient in a system, then this chemical potential gradient gives rise to an electrical signal, and this electrical signal can be a useful property because now you can use this electrical signal in practical devices like sensors, in fuel cells, in batteries as a tool to regulate something. Okay. So, regulate the chemical part of the system. So, now you have basically these two chemical parameters and electrical parameters which can be used to regulate the system. So, for example, now in an ionic system you can have a system in which you have, suppose you have a gradient in the oxygen concentration. So, this is something which happens very regularly in batteries or in many other devices. So, suppose you have a system. Okay. So, let us say you have some sort of device. Let us say this separates two regions. So, in this case you have some PO2, let us say PO2 1, and here you have PO2 2, and this change in partial pressure of oxygen requires, which means you have a gradient in terms of oxygen concentration. You might have a gradient like this, which means you have transport of oxygen in this direction, and this transport of oxygen, since you have a chemical gradient as a function of composition which is related to your electrical gradient, this gives rise to a signal, let us say V, and this ionic transport as a result of chemical potential can now be controlled by using this electrical signal. So, now what must happen in such a system is when you have electrical signal as a result of this ionic concentration gradient, you must not have an electronic conduction, otherwise you will have short circuiting. So, for these kind of applications one must ensure that Ti is equal to 1, which means Te is negligible, no electronic conduction. You would like to prefer a system where ionic conductivity is highest to avoid the short circuiting. So, consider now two systems where you have two sides separated by an electrolyte. So, we consider a system, let us say this is an electrolyte, or let us draw in the next page. Okay. So, the better picture would be something which I am going to draw now. So, you have such a system. So, this is let us say your electrolyte. It could be solid, liquid, does not matter. In most cases in ionic solids it would be solid. So, here you have PO2 1, here you have PO2 2. Okay. So, you have gradient in the oxygen partial pressure, you connect this with potentiostat, this gives rise to a potential, let us say phi. Okay. Now, what we will do is that, so what will happen at equilibrium? Now, at equilibrium, when there is a equilibrium there, so electrochemical potential of side 1 will be equal to electrochemical potential of side 2. So, let us say, which means I define eta I 1 is equal to eta I 2, because at equilibrium the overall electrochemical potential has to be equal. So, if this is the case, now we know what is eta I 1. Eta I 1, if you go to previous slide, is nothing but sum of these two mu I and Zi Fi. So, this becomes mu I 1 plus Zi F phi 1, okay, or delta phi 1. Similarly, eta I 2 becomes mu I 2 plus Zi F delta phi 2. Okay. So, I know the equilibrium condition is eta I 1 is equal to eta I 2. So, as a result, now I can write mu I of side 1 minus mu I of side 2. So, what I do is that I rearrange the terms. I take the chemical potential term on one side, electrical potential term on another side, and this becomes equal to 1 to 2 minus of Zi F d phi by dx. Okay. So, delta in the previous case this becomes equal to, excuse me, let us get this sign correct, this should be del phi by del x. Similarly, okay, this is fine. Here it should be like this. Here again we just make this signs correct, otherwise there will be confusion. So, okay. So, this becomes, now you have taken both of them on one side. So, chemical potential of side 1 minus chemical potential of side 2. So, here what I have done is this negative sign will come out, and this I have taken chemical potential of side, electrical potential of side 2 minus electrical potential of side 1. So, that is why this negative sign has come out, and this becomes equal to minus of Zi F, I can say if I am integrating it, it will become delta phi. So, this chemical potential now be written as so chemical potential, I know mu I is equal to mu naught plus half chemical potential of any species I is equal to mu naught plus half of RT ln. If I consider it as activity, then for oxygen it would go as PO2. So, since I am considering here oxygen, chemical potential gradient of oxygen. So, let us say this would be mu O naught. Okay. okay, because ith species I have taken it as oxygen here. So, as a result, now all I do is that I make substitution. So, this minus Z I F delta phi becomes equal to half. So, mu naught will cancel each other, because this I is nothing but oxygen, okay, in this case. Okay. So, this becomes half R T ln PO2 1 minus half R T ln PO2 2. Okay. So, as a result, this becomes equal to minus Z I F delta phi, this is equal to half R T ln PO2 1 divided by ln divided by PO2 2. Okay. So, this is your relation, or delta phi has become equal to minus of half R T divided by Z I F ln of PO2 1 divided by PO2 2, or delta phi is equal to half R T divided by Z I F ln PO2 2 divided by PO2 1. So, this is called as, what is famously called as, Nernst equation of electrochemical equilibrium. Now, what this tells you is that if you have a system in which you have a gradient of partial pressure of oxygen, this partial pressure of oxygen gradient across an ionic solid will give rise to an electrical signal delta phi, which is a voltage. So, this is a very useful thing. This can be used in, for example, controlling the air to fuel ratio in automotive application, which I will explain in a minute. Now, so this equation was calculated considering you have complete ionic conduction. Now, if you do not have complete ionic conduction, in that case this delta phi would be modified. So, if you have if your Ti is not equal to 1, if Ti is not equal to 1, then delta phi will be equal to Ti multiplied by half of RT ZIF ln PO2 2 divided by PO2 1. Okay. So, and Zi in this case, since we are considering oxygen ion transport, this Zi will be 2. So, for oxygen ions it would become RT divided by 4F. If the type of your ion changes, in that case this Zi will also change. So, this will be your this is the Nernst equation, whose message is, if you in an ionic solid, across the ionic solid, if you use ionic solid as an electrolyte, if you have partial pressure gradient of, let us say, oxygen, then this partial pressure gradient of oxygen, since oxygen diffuses through the ionic solid, it gives rise to an electrical potential which is delta phi, and this electrical potential can be used as a signal in various practical applications. So, I will give you one example, for example, automotive applications. So, in automotive applications, suppose you have this something in exhaust. Okay. So, this is, let us say, your exhaust plug. All right. Now, in this exhaust plug, you have inside you have air to fuel supply, and outside you have exhaust. Okay. Now, in the exhaust gases, typically partial pressure of oxygen would be anywhere between 10 to the minus 9 to, okay, and here inside this you will have PO2 approximately equal to 0.21 atmosphere. So, this is a massive gradient of partial pressure of oxygen. Now, if you take at a temperature, for example, at about let us say about 620 to 630 Kelvin, which is roughly nothing but your 350 degrees centigrade. Now, at these temperatures, this gradient of partial pressure of oxygen will give rise to delta phi of about 0.25 to 0.5 volts, and this voltage is sufficient to be monitored. It can be easily monitored, and this can be used in a feedback control system to regulate the air to fuel supply, because we know as this pressure changes, this will change. As this ratio changes, this will change, because the air to fuel ratio determines efficiency of combustion, would determine what is the exhaust gas composition. So, this concentration gradient across this, so this is nothing but your ionic solid. So, this concentration gradient across this ionic solid can be used as a tool by means of an output which is delta phi, which is reasonably large voltage, to regulate the air to fuel supply in automotive systems. So, this is something which is very useful thing, which can be used for variety of applications. So, at this point we are done with most of the concepts related to ionic conduction in solids. What we will do now, we will now have a look at some of the applications of these ionic conductors. So, ionic conductors can be used in variety of applications. So, for instance, ionic conductors can be used in some of the common applications are silicon carbide, molybdenum. These are used as heating filaments in furnaces. The resistivity of these materials is appropriate for resistive heating in the furnaces. They are also used as electrodes in some applications. Things like zinc oxide, silicon carbide, they are used as varistors or devices for circuit protection. Solids like yttrium stabilized zirconia, beta alumina, they are used as fast ion conductors. They are used in batteries and fuel cells. YSZ is also used in gas sensing applications. So, there are a variety of applications in which they are used. Now, you can see that for applications like heating filaments, one is more concerned with the electronic conduction, while applications like FICs and gas sensing, they rely more on ionic conduction. So, depending upon the type of application, you are interested either in electronic conduction part of the solid or ionic conduction part of the solid. Now, if you want to go into details of applications, since we can't cover everything in this course, you can refer to a book. So, reference for this part would be Electroceramics book by A.J. Moulson and J.M. Herbert, and this is a Wiley publication. So, this book is a very nice book which narrates various applications of electroceramic materials. In this remaining lecture, we will discuss some of the applications which are pertinent to us, and then we will finish this module. First example that I will take as is your varistors. Now, varistor basically means voltage dependent resistor. Okay. Now, this is a device which offers which is used for circuit protection, and what it does is it has very low very high resistance at low voltages when the device has to be operated, and when the voltage crosses a threshold, when it can fail, then its resistance suddenly becomes low. So basically what happens is so the operation is something like this. What it means is that the current which is flowing through the varistor at moderate voltages, so this is your IV curve, and then at high voltages it suddenly shoots up. So, this will be your threshold. So, in this section you will have low conductivity or high resistance, and in this section you will have high conductivity. And basically what you have is, you have a device which needs to be protected. So, this is your device, you put in parallel with varistor, and then you have a source. So, at moderate voltages, since the resistance here is high, all the current passes through here, but when the voltage becomes higher because of surge or whatever reasons, if your grid is not giving you reliable power supply, then in that case, when voltages become high, at that point the part of the current goes through this. So, protecting this device from things like surges in the circuit. So, the typical materials that are used for these applications are zinc oxide or silicon carbide. Now, basically what you have is a zinc oxide powders which are pressed together. So, majority of the medium is zinc oxide, and then at the grain boundary or at the boundary between two powder particles, you have a layer which is called as an intergranular layer, whose resistance is very high, and this high resistance allows the material to remain highly resistive at low voltages. When the voltage becomes high, then the conduction through these tunneling through these thin interlayers or intergranular layers starts. So, I'll now draw the. So, what you have here is basically these particles. So, this is your zinc oxide particle, whose diameter is roughly 10 to the 50 micron, zinc oxide or silicon carbide, and between these you have these intergranular layers. So, of course, I am making it a little bit more magnified. The intergranular layers are very thin in nature. Typically, these intergranular layer could be submicron. In fact, they could be nano sized range. So, these intergranular layers have roughly thicknesses of 10 nanometer to about a micron, and this could be made of oxides like for example, bismuth oxide. Between the zinc oxide grains, bismuth oxide or manganese oxide. Okay. So, which are insulating in nature. So, basically what happens is now this, how it happens, you can get an understanding through the band diagram, and this band diagram is something like this. So, you have in the equilibrium, so you have an intergranular region. Okay. So, this is your intergranular region. On either sides you have zinc oxide grain. So, ZNO on either side. So, now at equilibrium you have Fermi levels match. So, this is your Fermi level which will match at the equilibrium, and then of course, you have your conduction and valence bands. EV and EC. So, at equilibrium of course, nothing happens, but when the bias is applied, when you have large bias, what happens is, so for instance, you can assume a situation in which the grain on the right side is left side is forward biased. So, let us say this is your forward biased grain, this is your reverse biased grain. Now, forward biasing and reverse biasing you must know from the fundamentals of p-n junction. So, basically in a p-n junction forward biasing would mean, so this is your p-n junction, forward biasing would mean you make p type more positive. So, p type becomes positive and n type becomes negative, allowing the flow of current through the junction. Okay. So, this is forward biasing, and reverse biasing is the opposite. P becomes negative, p is connected to negative terminal and n is connected to positive terminal. So, I will not go into details of this. If you want to learn about this, you can go through any elementary solid state physics book. So, what happens in varistor is at high biases there is a forward biasing of one type of grain and reverse biasing of another side of grain. So, one grain, so at high biases one grain is for left grain, imagine that left grain is forward biased and right side grain is reverse biased. Under such condition, what will happen when this grain is forward biased, the barrier on this side will reduce, and so naturally, as you know from the fundamentals of p-n junction, under forward biasing the barrier decreases, and under reverse biasing the barrier for carrier movement increases. So, what happens here is the bands tilt on one side, the bands bend more on one side more than other side. So, as a result you have band bending. So, you can see that the band on one side are much more lower as compared to other side of the junction, and this with respect to the, so this would be defined as phi L, this would be defined as phi R, and here the Fermi level can be defined as, so since you have biasing, you have shift in the Fermi level, and distance of Fermi level from both of them will remain same, and this is your intergranular layer, in which whose work function is, let us say, phi naught, and the bias on right side is nothing but V R, and bias on left side is nothing but your V L. So, and of course, you can plot the intrinsic would be like this. So, this would be E F I. Okay. So, what happens here is in the intergranular region you have filled acceptor states. Now, as a result, what you can see is, since you have band bending taking place, you have tilting of bands on, you have bands on the one side raised, another side you have bands lowered. As a result, you have tunneling of carriers through the intergranular junction, which allows the current to flow in one direction. So, across the intergranular layer. As the, what happens as the voltage, as you increase the voltage bias, the phi L decreases because these bands go up, and phi R increases because these bands go down, and this leads to lowering of barrier on one side, and this leads to conduction towards your in this direction. Okay. So, so basically a whole mass of material looks like as if you have network of diodes in a circuit, and with each, so and you have a pair of diode, basically one pair of diode is, one is, and out of this pair one is forward bias and one is reverse bias. So, that is what happens in whole material all across. So, when you have very low bias applied, then nothing happens because the barriers are not very, the change in the energy levels is very small. As a result, nothing happens, no current flows, and when voltages are high, then junction breaks down. As a result, you have thermionic animation due to tunneling across the junction due to band bending. So, this is what is basically a varistor. Now, second application which is there is a solid oxide fuel cell. So, you have solid oxide fuel cells, or they are also called as SOFCs. Okay. Now, these SOFCs are nothing but your energy conversion devices, which are based on electrochemical principle. And so, basically you have, what happens here is you introduce a fuel which gets oxidized and which gives rise to production of electricity. So, one of the principle of operation basically is based on, you have, so this is an electrolyte or an oxide, let us say. On either side of this oxide you have electrodes. So, this is your, in case of oxide fuel cell you will have an oxide. So, and this is your, let us say, anode, this is your cathode. Now, what happens in these is, so you introduce air from this side, and this air provides basically the oxygen, okay, and through this oxide you have O2 minus conduction, and you provide fuel from this side, and typically let us say the fuel is hydrogen, okay, and this hydrogen reacts with oxygen, giving rise to excess water. So, H2O plus unused gases, because gases may not be burnt completely, or let us say in this case unused fuel, and here you will have unused gas, which could be nitrogen as well as oxygen, not all of it is completed, and this is your, this acts as your electrolyte, which is nothing but a hard porous ceramic which allows the ionic transport. Now, so the reactions here which take place are, so if you have for instance anodic reaction, so reactions at anode, if you have hydrogen as a fuel, then H2 plus O2 minus, giving rise to H2O plus 2 electrons, and if you have CO, then this is CO2 plus 2 electrons. This is your anodic reaction, and your cathodic reaction would be, in this case, O2 plus 4E 2O2 minus. Okay. So, now you can see, if you put, this is an electrical circuit. So, you have creation of electrons here at this anode side, and electrons go like this, and electrons are consumed on the cathode side when they react with oxygen to give rise to oxygen ions, which are then transported through electrolyte towards the anode to complete the whole circuit. So, this is the basically the circuit diagram, and you can now write the overall reaction. The overall reaction is nothing but production of water, and you have CO plus half O2 giving rise to CO2. So, these are the overall reaction, but electrochemical reactions are these. So, this is your anodic reaction and this is your cathodic reaction. On anode, electrons are liberated, on cathode electrons are consumed. So, this is what is the principle of solid oxide fuel cell operation. Now, a device of, so naturally when you have, now this device does not give rise to high voltage. So, in order to have reasonably large power, you need to connect many more devices in with together. So, as a result you have a lot of technological issues like how the devices are connected, how they are packaged. So, in the device form, what you have is basically you have something like this. The cross section looks like, so you have an outer shell, okay, and this outer shell is nothing but the outer electrode. Okay, and then you have So, if I shade it like this, this would be your outer electrode, and then in the middle you have electrolyte. So, this will be your electrolyte, and then inside you have another layer of this yellow thing is your electrolyte, and this inside thing is your inner electrode. So, what basically you have is, on one side you have fuel flowing, another side you have air flowing. If air goes here, then fuel goes on outside. So, this is a cylindrical body. So, it would be like this, and on top of the cylindrical body you will have an interconnect which would connect with other devices. So, and these interconnects are in such a manner so that they improve the device performance. So, basically you can use various kinds of materials for such purposes. Your anode material is typically porous nickel. Cathode is typically it has to be, so porosity is very important here. So, cathode is typically a porous p type semiconducting oxide, such as lanthanum, strontium, manganese oxide, LSMO it is called as, and interconnects are typically your either it could be stainless steel or it could be some doped oxides. So, interconnects are typically SS or doped steel. These devices are very useful devices. They can work over large temperature range, but they work at high temperatures. So, typically the working range is somewhere between 700 to 1100 degrees centigrade, and they could have an aerial resistance of roughly 1 to 2 micro ohm per meter square, and they work on a very large range of oxygen partial pressure down to 10 to the minus 20 atmosphere, and the efficiency of these devices is roughly 60% at 1000 degrees centigrade, and this gives you output power of about 100 kilowatt hour. So, these are some facts related to these devices, but this is a very useful application of conducting oxides. Now, the third and last case that we will discuss here is the oxygen sensor. So, oxygen sensor, as we discussed, it has a design like this, and this is your ionic oxide or ionic solid, basically which has high. So, you have partial pressure of oxygen 1 here, PO2 2 here. Typically, you will have air to fuel ratio supply here, and outer side is exposed to exhaust gases, and this differential oxygen partial pressure, because now air to fuel ratio in case of automobiles 14.5 is the optimum. Okay. Now, what happens is that above this ratio the burning in such a manner so that hydrocarbons and carbon monoxides decompose efficiently, but below this you have NOx gases which burn efficiently, but carbon monoxides and others do not. So, as a result you need to maintain this ratio quite reasonably well. Now, this is where when you take the signal between these two sides. So, you put contacts on these two sides, connect to electrical circuit, maintain the potential, measure this potential, use this potential through a feedback loop circuit to regulate the air to fuel supply because you would know when you have absolutely efficient burning what should be the ideal or reference point. Compare that with the reference point and correct the air to fuel ratio accordingly. So, this can be used in a fuel injection system the principle is based on electrochemical potential, and this can be used to regulate the fuel supply. So, these are some of the applications of ionic solids from their conduction point of view. So, this ends the module 3. In the next, so what we have discussed in this module is basically we have tried to relate parameters like diffusivity with the conductivity, and we have looked at a model of conductivity, looked at various conducting ionic solids, and some of the applications. So, this gives you a reasonably good summary of or overview of ionic conduction in solids. Now, this finishes the module 3 here. In the next module, which will be now module 4, we will start looking at completely other side of the spectrum. Now, in the next class, what we will learn is what is called as insulating oxides, which are nothing but your dielectrics or capacitors. Okay. Thank you.